We are happy to have today Professor Ling-Yan Hung from Fudan University, and she works in many things. She is expert in holography, DSFT correspondence. Also, she works extensively on these topological phases, etc. And today she will talk about some aspects of Anyon condensation. So I will hand it over to Janet to start the talk.
So thank you very much, Apan and Sudipto, for giving me an opportunity to speak here. So I was trying to move the stuff away. It's blocking my view. Okay. So so what I'm going to talk about today is something called Anyon condensation and some of its applications. This is something that we have spent a lot of time in the past couple of years, and it has quite a lot of applications, as I'm going to show, particularly in when people study topological phases of matter. Anyon condensation is an important physical phenomena, theoretically, it's a very useful tool in constructing maps between these different theories. Physically, it's very useful because it really is a physical phenomenon that describes interfaces between different phases. And on top of that, because of the connection between topological theories and CFTs in one lower dimensions, it also help us to understand things like topological defect operators, topological operators in a CFT, or understand modular invariance in a CFT. So it has many tentacles, so I want to be extremely pedagogical here. So please stop me at any time if anything is unclear. So what I want to describe for you is what exactly is Anyon condensation, what is the mathematics that people use to describe this stuff, and how do we apply these mathematics and extract physical results. Okay. So what is the outline of my talk is that I will start with reviewing what is topological order, and I'll focus particularly in 2+1 dimensions. So the reason why we focus on 2+1 dimensions is that the mathematical results are most complete in 2+1 dimensions. If you go to higher dimensions, in principle, it is still possible to talk about topological interfaces, but our understanding of it is not so complete. And so I will describe for you a more complete story in 2+1 dimensions. So I'll talk about topological orders in 2+1 dimensions. Then I will start talking about Anyon condensation that happens in each topological order. And I'll show you why by considering Anyon condensation. It is a way of connecting different theories. It's more or less like these Russian dolls, where you have a theory living inside another theory, and it can go on forever and ever, one inside the other. It's really a web of theories connected with each other, it's basically, you could also understand as algebra embedded in another algebra. So in a way, as you're going to see, Anyon condensation is a description of some algebra. And these webs of theories are basically telling you that the symmetries of these theories are connected by embedding an algebra in another algebra. And then I will show how these things are connected to things in CFTs. And then I will try to summarize and discuss some future problems that are of interest. Okay, so let's start with topological order in 2+1 dimensions. The most well-known examples of topological orders in 2+1 dimension is the fractional quantum Hall effect. And so So what exactly is this term topological order about? I think it was coined by Xiaogang Wen back in the late 80s and early 90s. Why do they call that topological order? Because in the case of these, for example, this fractional quantum Hall effect, you get a phase transitions as you switch to different transverse magnetic field. But these different phases, they preserve the same symmetry. These different phases are not separated by a phase transition characterized by symmetry breaking, as in the case, as we usually understand it in this Landau symmetry, Landau effective theory that describes phase transitions. And therefore, it inspired the term topological order to say that these phase transitions has nothing to do with symmetry breaking, and there's something, and also the properties of these phases there's something long range entangled or long range correlated about them. So some of the hallmark of these phases includes Anyon excitations, excitations with fractional charges. So that is a hallmark of non-local, being a non-local excitation. Why? Because as we know, anyons cannot be excited by itself alone, and whenever it is excited, they have to be excited in pairs. And so it means that this excitation, even though it looks local, there's something non-local about them, and they're not allowed to be created by themselves. And these anyons, they exhibit highly non-trivial statistics, fractional statistics, or even non-abelian mutual statistics. Also, we know that if you put these theories on non-trivial manifolds, let's say consider a state where you put the topological order on a torus or on a homogeneous surface. So I'm talking about a constant time state. Then there is non-trivial number of ground states for any given manifolds. So that is another hallmark that there is something long range correlated. Why? Because these different ground states, if we try to describe some of these effective theories for these topological orders are something like Trans-Simons theories, and so these are non-trivial ground states. You could think of them as carrying different anyonic. The anyons can, the world lines of anyons can wind on non-contractible cycles. And so by using these Anyon line operators, you can construct different ground states. We'll see more of that shortly. But the bottom line is, these windings, you can only be able to tell whether there is non-trivial winding if you go in full circles around those non-contractible cycles. And so it means that in order to distinguish these different ground states, I have to make measurements that has to be as big as the manifold that I live in. And so this is another hallmark that there's something very global about these phases. There's some long-range correlation in these phases. And this long-range entanglement can also be viewed but when you compute things like topological entanglement entropy, as discussed in Kitaev, Praskal, and Levin-Wen. So these are some basic things that we know about topological orders in 2+1 dimensions. And so what is the mathematics that describes the physics of topological order? So one very useful way of summarizing the most important properties of a topological order is to use the mathematics of modular tensor categories. So what are these things? So they're not complicated things. In fact, they are very simple. So they're basically capturing the most basic ingredients that go into a topological order. So what are these most basic ingredients in a topological order? As we just mentioned, there is the notion of anyons. And anyons in a tensor category would correspond to some simple objects, so a tensor category. There are several ingredients. The first ingredient, the most basic ingredient, is to have a list of stuff, a list of objects, and physically they correspond to a list of different species of anyons. For simplicity, in cases where we can work with very systematically, we restrict to rational systems or rational theories, where the number of simple objects is finite. And so that corresponds to a case where the number of different anyons, number of different species of anyons is finite. So what can anyons do? And each of the things that you can think of anyons doing is one extra mathematical structure in these tensor categories. So what do we know that anyons can do? They can fuse. If two anyons are very close to each other, and if I'm very far away, then it would appear to me that these two anyons is just one anyon. I can't distinguish them apart. And in general, these fused anyons can be decomposed in terms of the simple basic species that is already in the theory. So if it is a rational theory. And so in general, there would be a linear map. So in the mathematics literature, they would call that homomorphism. But really, it just means a linear map in Hilbert space between the space where there are two anyons, A and B, and the map and anyon C. So if A and B can fuse to C, so if A cross B can be fused to C with certain number in n different ways, n a b c different ways, then I would be able to construct n a b c different maps from A, B to C, and pictorially is represented in this way. So constructing these linear maps is basically to a mathematical structure that you put into a tensor category to say that okay, the fusion corresponds to a set of linear maps that I can construct. Okay, so what else can you do with anyons? So we talked about non-trivial statistics, and therefore you can. So statistics is basically to allow one anyon to be to move around the other, and so this is another mathematical structure that I can put on top of my tensor category. I would define a crossing and claim that this crossing is proportional to the one without crossing up to a face, because this is just statistics. I move around something, I would get a face, so this is a second structure that you put. And modular tensor category is basically just some category which can fuse and which can braid. And modular means, as I'm going to show shortly, it corresponds to certain requirements on the braiding structure. But why is tensor category useful? It is helping you to arrange this data that you put in. You claim that things can fuse, you claim that things can braid. So there might be some consistency conditions that allow things to fuse and braid at in different orders, and they still make sense. So tensor category is a way to help you to arrange this kind of data. So what kind of consistency can you think of? So first of all, we're talking about fusion. We know that if I have three anyons that are very close together and I'm from very far away, then I should be able to see that, okay, these three things looks like it is just it can be decomposed into certain charges, certain excitations that are already in my simple set. So it shouldn't matter whether if I have three things, A, B, C, whether A, B fuse together first and then fuse with C, or B, C fuse together first and then fuse with A. I should be able to, from afar, I should be able to detect exactly the same thing. And so there is the notion of associativity in this fusion. And so in particular, we would say that if, so pictorially, it is represented as the linear map from ABC to D, if I can be decomposed into first fusing A and B to E and then fusing E with C to D. But this order of fusion should not be linearly independent of this order of fusion where I first do B and C and then finally with A. So they should be related, and the coefficients that relate them is the so-called 6J symbols. And so now this comes to a consistency condition called the Pentagon relation, where I have 4 objects, and I could consider first fusing B and C, and then first fusing, so I could do this is often called an F move, where I change the order of fusion. I started with this order of fusion, but then I decided to change it to fusing B and C first. And then moreover, I further do another F move. So I can do 3 F moves to get to here, to get down to this fusion order. But at the same time, I can do something different. I could move C to D first, and then I move this link down by another F moves, and it would reach exactly the same basis. And so if the theory is consistent, it better be true that these coefficients satisfies the so-called Pentagon equation, because there are 5 pictures in this loop. So a product of 3 different F's that you collect along this path has to be equal to a product of 2 F's that you collect along the other path. So this is the so-called Pentagon relation. So this is one consistency condition that you put onto your tensor category, but really it's basically some very fundamental consistency conditions that you have to include in your in a theory that describes fusion, that is associative. Moreover, because you have braiding, so you allow lines to cross over each other, and so we can play the same game. I can have some crossings, and I can basically move things around, and I could reach the same a picture using 2 different paths of either braid first and then change the order of fusion, or change the order of fusion and do a braiding. And so again, this gives me the so-called hexagon relations, another consistency relation that relates your braiding data, the phase that you collect when you have an anyon over another, and also these associativity coefficients. So this is the so-called hexagon relations, because there are 6 pictures in this relation. So this basically is the basic fundamental constraints that you need to put in for any theory that describes something that can fuse and braid. So that tells you so much about braided tensor categories. So, and what is a modular tensor categories? So modular tensor category is some extra conditions that you put on the braiding structure. So in particular, I consider putting your state on a torus. So this is a 2 + 1 dimensional system, so I can construct states on a 2-dimensional Riemann surfaces. And in particular, let's consider a torus. So the number of different ground states is basically, you can construct a basis for this ground state by considering anyons that wrap around the non-contractible cycle. And so the ground state degeneracy would be simply equal to the number of different species in the theory that I could put around this non-contractible cycle. But we all know that on a torus, there are some modular transformations that keep the torus invariant. So when I do a modular transformation on these ground states, I might be changing basis so that these different ground states would be rotated into each other. I should preserve the ground state space of states, but in general, when I do a modular transform on the torus, I might be rotating these states among themselves. So how does it rotate? If I have an anyon wrapping one of these cycles, and if I do a T transformation, the T transformation corresponds to, if I if I stare at this torus, it corresponds to more or less like drying towel, twisting it in the in the so basically I hold onto the holes and twist it by one cycle. So that keeps the torus basically invariant. But then what happens would be that the anyons basically wrap around the orthogonal cycle once. And this extra wrapping around, so this anyon, after I do the T twist, what it does to the anyon line is basically it creates this twist. Of course, the ends are then joined again in the other cycle. So what exactly is this twist doing? This twist is basically that the anyon moved around itself by one circle. And so that just gives you the self-statistics of the anyon. So it gives you a phase. It keeps you in the same phase, in the same state, but with an extra phase. So anyon wrapping in this cycle is an eigenstate of T, which shear in the orthogonal cycle. And so in particular, if it is a boson, if A is a bosonic anyon, then e to the I theta is just equals to 1. And if it is, but in general, these are anyons, so e to the I theta could be any phase. Then another important quantity is that I can rotate the anyon by, the torus by 90 degrees, flip it from this direction, and so the anyon line would be flipped to the other cycle, and you can decompose this anyon wrapping the other cycle. They're not independent in terms of the anyons wrapping the original cycle. So SAB, you can think of it as the overlap between the A cycle, anyon wrapping the A cycle, and anyon wrapping the B cycle. So if I draw a picture that represents SAB, you could think of it as basically the overlap of an anyon wrapping the first cycle and an anyon wrapping the other cycle. And you see, this picture really corresponds to B moving around A. And so you can think of SAB as some kind of mutual statistics, the phase that you gain when B runs around A. And being a modular tensor category means that SAB is a unitary matrix. That is an input data that you put into the theory. Audio are not clear. Is it still unclear? I'm so sorry. I didn't see
so
the.
I think for me it's clear. Maybe you speak closer to the microphone. That's
Okay. I'll speak closer.
Can I use this time to ask a question, Ling, since you got already interrupted? I'm a little bit, I think, so this transformation T and S, they seem to be slightly different in the sense that S seems to rely on having the torus embedded in some other higher space, right? So the T seems to be something that is sort of inherently, I can talk about it as some shear of the torus itself, whereas S seems to, if I understand correctly, S seems to be like either, let's say, if there is a 3D space in which this torus is embedded, going from XY plane to some orthogonal plane. Is that correct?
Because you think, I think you don't have to embed it into high dimensional space to understand S. It's still intrinsically that you basically so you have two cycles, right? And you can't really distinguish which is which. And S is just saying that the two cycles, I flip them, and I'm describing exactly the same torus. So I don't think you have to embed it in high dimensions to understand.
Okay, thanks.
Right. Okay. So I can't flip my page. Oh, yes, I could.
May I ask a question, please?
Yes, please.
Could you? I'm kind of confused here because you said that I thought the anyons, the way you introduced earlier, seemed to be the excitations over the ground states. Is that not correct?
Right, they are the excitations of the theory.
But then what does it
But
mean if
they
you go
can.
back to the slide?
Okay.
But when you said that ground state degeneracy is equal to the number of anyons, is that
Very good. So if I
so? How does that
right,
come
very
about?
good, very good, very good. So when you say, so I think it is best illustrated, let's say, in Trans-Simon's theory. So if I have, so when people say there is an excitation, they really mean that I can, oh, I want to draw. Okay, annotate. Okay.
Maybe you can draw on the board behind.
Somehow I can't flip my page anymore. Okay, I see. If I start annotating, I can't flip the page. I see. Okay, now, okay. So if in Trans-Simon's theory, we know that the degrees of freedom is the field variables A mu, right?
Right.
And if I, so gauge invariant quantities, basically we have some Wilson loop, right? But if the Wilson loop is contractible in a Trans-Simon's theory, then it's trivial. It doesn't do anything to the state. And so these ground states degeneracy corresponds to Wilson lines of different representations that wrap around this non-contractible cycle. So even though it's a flat, there's no gauge non-trivial, it's a flat connection, it still gives rise to a different ground state. When I say excitations, what it means practically is that we're considering some open Wilson loops. And so so Trans-Simon's theory as an effective description, they are completely equivalent to to this topological order as far as the ground state, the gauge invariant excitation is concerned. But the physical excitation that you actually see, you could think of them roughly as, I can't see my cursor. Where is it? Somehow my cursor disappeared and I can't control where to draw. That's weird.
Actually, this writing is still coming, actually.
Sorry? I can't see my cursor and I can't stop.
Restart this slide one more time. Close this and share the screen.
Okay, so maybe I should stop share and then. Okay, now I see my cursor again. Sorry.
Just one thing. Do you think it'll be easier for you to? Because I see a whiteboard behind you. Do you think it'll be easier for you just to draw on the board? It's just...
Oh, that's not a board. That is just my wall at home.
Okay. I wouldn't suggest you draw there.
Sorry about that. Now you make me feel like I really should buy a blackboard at home.
Well, that's
sorry about that. Okay. Now I can. Okay, I think I'm able to draw. Okay, maybe in this way. Okay. This Wilson. So when we talk about excitations, it really corresponds to open Wilson lines, where then these endpoints of the Wilson lines, strictly they're not gauge invariant, but I would be able to detect them, detect these endpoints, and so. When I have excitations, I'm away from the ground state subspace. The way to represent the excitations is by considering more or less open Wilson lines. But when I'm constructing ground state bases, I'm considering non-contractible closed Wilson lines. So that is how the correspondence between anyons and these ground state bases is comes about, and therefore it becomes the number of ground states that you can construct precisely corresponds to the number of different species of anyons. Is that somewhat clear?
Yeah, it's a little clear. Yeah, thanks.
Okay. So what I have described for you is the basic premise of a tensor category. So let me give you one very simple example that I'm going to use again and again. And this is a so-called Z2 toric code. So the easiest way to understand this model is that this is really a Z2 gauge theory. And you have the trivial sector, which is just a vacuum, there's nothing. And then you have the electric charge. The electric charge is the Z2 charge. M is the magnetic charge of the magnetic flux of the Z2 gauge theory. And F is the bound state of E and M. And this topological spins or self-statistics of these four sectors is that one, a trivial, of course, it is bosonic. The electric charge is bosonic. The magnetic flux is also bosonic. And the bound state is fermionic. So roughly, how do I, so S, it gives you the mutual statistics, and these numbers are pretty easy to understand. So for example, here, this line, it says if E moves around the identity, you get basically a trivial phase. M moves around the identity is trivial. Everything moving around the trivial sector is trivial. What about this -1? This one says if I move an electric charge around a magnetic flux, since this is a Z2 gauge theory, if I do it once, I would collect a phase of a -1. And similarly, if E moves around the bound state of E and M, since E moving around E is trivial, so E moving around the bound state of E and M gives you -1. So this is how the S matrix is understood. It's basically giving you the mutual statistics. And you can check that with appropriate normalization, that is related to so-called quantum dimension of the model, this is a unitary matrix. The fusion rules, because this is a Z2 gauge theory, E fused with E is just identity, similarly M fused with M, but then F is an EM bound state, so E fused with M is equals to F. So this is the simplest possible modular tensor category that you can find. And I'll use it to illustrate this concept of Anyon condensation shortly. So, okay, now comes to the concept of Anyon condensation. So, if I want to consider a slightly different phase, and if it happens that there is a gap or topological interface between these two phases, what would be the relation? How do I get from phase 1 or phase A to phase B? So the idea is, one way of getting from A to B is that maybe something condensed, exactly like the Higgs mechanism. Then phase A would change to something else. So when we talk about condensate, it really corresponds to taking a collection of anyons in A and say these things, initially they are conserved quantity. Each of these anyons, the number of these anyons is a conserved quantity. Is a conserved quantity. You cannot create. Well, okay, they could an anyon and its and the anti-anyon can annihilate. But if I have an isolated anyon, that is the number of that species is conserved. Now we are saying that no, these guys condense exactly like Cooper pairs or in a superconductor. The number of Cooper pairs are no longer condensed. I have a bath of that. And so you have to first decide what is the number of different species of anyons that are no longer conserved, that they condense. And so there's some consistency constraints that you have to put in order that these anyons can condense. For example, these things are better bosons for them to condense. We know that things like fermions or let alone objects with arbitrary statistics can condense. And so these objects better be bosons. And so imagine if these objects condense, then how do I predict the properties of the new phase of matter? If this guy condense, it means that in the new phase, it would be undetectable. It would behave like part of the vacuum, right? That's what condensation means. And so, moreover, two anyons if I could get, if Anyon 1 fused with something from the condensate becomes Anyon 2, then 1 and 2 would become indistinguishable from the point of view of the condensed phase. So you would expect that I could work out the number of the list of objects in B, starting from the objects in A. I just need to know which and which are identified under fusion with the condensate. So this is the basic idea. It's more or less like it's basically identical to the Higgs mechanism, and that the objects are some kind of representations of some symmetry. And now under the condensate, several representations would combine together to form a bigger multiplot. And this new multiplot would correspond to the objects in B. But then not all the multiplots actually would run around freely in B. So among the things that, so first of all, things in B can be written as a sum over objects in A. For the reasons that I described, you have to rearrange the objects in A so that they combine into some bigger multiplots in general. But not all of these combinations can run around freely in B. Why? Because remember, we have not statistics. This model is characterized by non-trivial statistics. So if so these C are non-trivial anyons, and some of these anyons, some of these other anyons that are not condensed, when they move around C, they might have non-trivial statistics. They might gain some in non-trivial phase. So it means that so physically, how do I gain a phase? It means that there must be some non-trivial, I'm creating some excitations. There's some non-trivial dynamical phase that is being generated. So it means that it costs energy for these anyons to run around in the condensed phase. And so it means that whenever I have non-trivial statistics between an anyon in A and one of the condensates, these anyons that have non-trivial statistics with respect to the new vacuum that defines B must be confined. They're no longer allowed to move freely. It's energetically expensive to create these anyons that could run around in B. So they becomes confined. So anyons in A appears in B. So these confined things would be stuck at the boundary between A and B. But then there might be other anyons that have trivial statistics with the condensate. For those anyons, they would be able to move to B seamlessly, and so we can basically separate all the stuff in A into two parts. Either they're confined and they would be stuck at the interface, or they would run freely in phase B. So what we have is that when C condense, I would have a new set of objects. This set of objects is a rearrangement of combinations of A. It's a linear sum of, it's a direct sum of objects in A, and they would be able to fuse in general. But then only a part of it can run wild in B, which means that B is running wild means B is a braided tensor category. It remains that you can still define braiding, have one object moving around the other, but not all the objects in beta where braiding is well defined, because some of them are not local with respect to the new vacuum, and among the objects inside beta, they can fuse. It makes sense to fuse them, but then only part of it you can still define braiding. So that is basically Anyon condensation connects a braided tensor category A to another braided tensor category B with some intermediate fusion category. Fusion category means only fusion is defined and braiding is not a well-defined quantity. So Anyon condensation is physical. It literally corresponds to having non-conservation of certain anyons. You can build Hamiltonians that such that you start with a topological order, let's say the Toric code. I'll show you an example later, and then you can build up a Hamiltonian such that some of the excitations, let's say the electric charge in the Toric code model, becomes non-conserved. It can the new ground state is such that there is an that is not that it's a sum over electric charges with different numbers. So electric charges is no longer conserved, and then in the new theory, you get a new braided tensor category, and some of the stuff in A would become confined. So this is a physical process. It is also some mathematical process which connects several different theories. Some with braided structure, some without braided structure. Some preserving only some fusion structure. And so it's really like a Russian doll. You start from one theory, it condenses, it goes to a different theory, and the interface between theories would basically be described by the fusion category, which can the fusion category beta, where things can fuse, they're stuck along this line, and then C2 would be a new fusion, a new braided tensor category. If I condense it further, it can go to C3, and then and so on and so forth. And so it creates a web of theories. So let me also note that Anyon condensation is, so we talked about interface, but in the special case where C2, if C1 is some non-trivial phase and then C2 is trivial, it only has one sector, the trivial sector, and no other sector at all, then this interface is really a boundary. Rather than calling it an interface between two categories, it really is just a boundary. But you see, any interface can be understood in terms of the physics of a boundary, because I could always imagine folding C2 into C1. Then what I was calling an interface is equivalent to the boundary of C1 cross C2 bar and nothingness. And therefore, if I understand completely what happens in the boundary, I basically know everything about interfaces as well. So that is called the folding trick. So how do I, so I described the physics, some basic understanding of Anyon condensation. So let me give you an example before I move to the mathematics. I'm a little bit slow, I'm sorry. So in the Toric code, remember we have 1, E, M, and F, 4 sectors, and E and M are bosons. So in principle, these things, either of them can condense. And indeed, there are well-known 2 different examples of boundary conditions for the Toric code, either where the electric charge can condense, and there's another boundary condition where the magnetic charge can condense. So each of them characterize a different boundary conditions. They cannot condense at the same time because they have non-trivial mutual statistics. And in particular, if the electric charge is condensed, then M and F would no longer be distinguishable, because M fusing with E is equals to F, and so M and F are no longer distinguishable. And moreover, M and F have non-trivial braiding statistics with E. They have a statistics of -1, and therefore M and F would be confined in the condensed phase. And so we call this new object where M and F are no longer distinguishable, we could call it X. And this X would be at best stuck at the boundary. It cannot move further because it's confined by the condensate. And when you take M fusing with M, you get the identity. And so it tells you that X, being where M and F are no longer distinguishable, the fusion of X with itself is always the new identity. It could either be 1 or E. And therefore, we say that the fusion category characterizing the boundary between the Toric code model and the vacuum is characterized by a Z2 fusion category. There is some object X that fuses with itself to get 1. So this is an illustration of how Anyon condensation works. So let me also bring to your attention that if you take the modular matrix of the modular matrix, and you take S1A plus SEA, so 1 and E are the condensate, you find that you go back to 1 and E. So it means that if I have something that is a 1 plus E, and then I do if I take the ground state of an Anyon 1 and E, and then I do a modular transform, it would basically go back to itself. Remember, S is the transformation matrix that goes from that do the transformation for you for the ground state. So it tells you that 1 and E being allowed to be a condensate, it would also generate for you a modular invariant. The ground state of 1 and characterized by Anyon 1, and the ground state characterized by Anyon E on a torus. If I do a modular transformation on this torus, then I would recover the same ground states. This is what it says. And this is important because when I start talking about the connection with CFTs, this thing is precisely how modular invariant CFT would come up. So let me speed up a little, or a lot. So I told you the physics of Anyon condensation. There's actually a very rigorous mathematics to describe these condensates. And what it is that it forms something called an algebra in the modular tensor category. So what it means? So there are several. So whenever you deal with tensor category, it's always the case that there would be several structures that you put into some stuff, and every time you put in an extra structure, you give it a name. So algebra just means there is some structure. So what is the structure that you call it an algebra? So the first thing that you need to do is that you have to find a collection of objects in the theory or in the tensor category. That is the condensate. So here, the algebra, I have to first decide upon a set of anyons. So these are the anyons that can condense. And being an algebra means that I should be able to determine a product of these objects. So remember, all the fusion bases have already been determined. They are this kind of pictures where C1 and C2 can go to C3. So when we say we want to determine an algebra, we're just basically determining this kind of linear coefficients that we're free to pick different coefficients to define this collection of bases of fusion between C1, C2, and C3. So what this is telling you is that when I have some condensates, they are going to condense, it better be true that when one condensate fused with another condensate, it would generate another party in the condensate. I don't want to fuse two condensates and generate something else. So this algebra is just telling you that there's actually some linear combination where C1 and C2 fuse together to give you another member in the condensate. Otherwise, it doesn't make sense for them to condense together. And also, so I will tell you shortly how to determine these coefficients. Then there's also this structure called coproduct. And coproduct is you can think of that as the inverse of the product. When you have, here you have a product of two anion that comes back to, that fuse to a third anion. A coproduct is the opposite, where I started with one anion and it splits into two. And again, I would have some coefficients that characterize this coproduct. So then you ask yourself, what kind of physical conditions that I should put into these coefficients so that it makes a sensible condensate? And the idea is that first of all, because they are a condensate, it better be true that when they are fusing together and I change the order of fusion, I shouldn't get new phases because this is just a vacuum, as if there's nothing. So if I have something non-trivial and I change the order of fusion, it might be possible that I get these 6J symbols that I introduced before that give me a linear relation between different orders of fusion. But if A is now an overall object, which is going to be the new vacuum, it better be true that I am able to change the order of fusion and nothing happens, no phase. And so how you choose these coefficients is basically that you have to choose it until, so you expand this A in terms of C1, C2, C3, and then when you change the order of fusion, which controls the associativity property of the C's, you get some 6J symbols showing up. So you have to tune these mu's and deltas so that at the end, this overall linear combination does not change under change of order of fusion. Also, as we already mentioned, it better be true that different anyons, when they run around each other within the condensate, they are local with respect to each other. So this locality is this commutative part. This trivially associative is this symmetric Frobenius part. And then separable here corresponds to the fact that I can create two vacuum. So A is now part of the vacuum and then annihilated again, but this is like doing nothing. And so it is like nothing happened. So this is another consistency condition, very natural, that you want to put onto your condensate. And this condition is called separable. So again, you can see that every single word here just corresponds to one extra constraint that you put into your theory, and then for each of these extra constraints, it corresponds to some algebraic equations that you want to solve to recover the structure, to recover the structure of the product, the structure of the coproduct that satisfies each of these qualifier. And so and moreover, so this is how we determine practically, mathematically, these condensates in a given. So in order to tell whether a collection of anyons can condense together, these are the physical constraints. So you go back and you take this set of anyons and you try to solve for these numbers that would satisfy all these conditions. If you manage to find these numbers, then it means that these anyons can in fact condense. And if no such solutions exist, it means that these anyons cannot condense together. So this is how you determine whether an interface or a gapped boundary can be characterized by the condensation of some of these anyons in a mathematical way. Then how do I determine what are the excitations that are allowed that are on the boundary? So I already mentioned, when I have an anion fusing with some part of the condensate, it might get related to another anion, and it should form a bigger multiplet. So what that means is that the excitations, the boundary excitations, are really representations of the algebra, of this algebra A. So in particular, you can solve for these representations. So in general, there are some anyons in A. Sorry, not in A. I mean in the bulk theory C. And now we say that this algebra A has some action. That it can act on these anyons, so it can fuse with these anyons, but maybe with some non-trivial coefficients. And C1, C2, I would have to sum over all the members in a given representation, in a given multiplet. And what would you expect this representation matrix that depends on C1 and C2 to satisfy? Being a representation, it must mean that if I act on A 2 times, it must be equivalent to first multiply the A and then acting on the representation. This is exactly what you do when you try to look for group representation as well. So what you do is that now you have defined you have defined an algebra. You go and look for all the representations of this algebra. Then you would be able to recover all the excitations at the boundary or at the interface between two topological orders. So that really gives you some practical way of working out the physics of these different theories related by a condensation. So these are just some details. You can also define fusion rules. When I have a product of two representations, in general, it can be decomposed into irreducible representations. And how do I work out this irreducible? How do I work out this product representation? So when I have two representations, the action of the algebra, you have to use a coproduct to split it so that they act on x and y separately. So this picture might look foreign, but it's actually very familiar. Think about if I have two spins in SU2 and that rotates under SU2. When I say I have a product of two spins, how does SU2 act on it? I would say, oh, J, the total angular momentum, is equals to J1 plus J2. So remember, this is in the Lie algebra. So in the group action, it is J, some rotation, is equals to exponential alpha J1 exponential alpha J2, right? This is how we act. A rotation is acting on a product of two spins. It's precisely to split one group element into a product of two group elements, which is the simplest example of a coproduct. And so when we talk about fusion of a product of two representations of this algebra, we're basically saying that now the action of this combined system can be determined by the coproduct of A and into 2A. And then this guy, you can then decompose it into some irreducible representations. It works almost exactly like group symmetry. And so these kind of things can be solved. So using this mathematics, you can basically start with any modular tensor category. You would be able to work out classify all the interface or boundaries, gapped boundaries of this topological order, and work out all the excitations that are allowed in this topological order. So what happens if I have two boundaries? Then now this algebra can act from the left. A1 can act from the left. A2 can act from the right. And so so to find out all the excitations that are localized at the junction between two boundaries, these are really so-called bimodules or bi-representations of this algebra. So it has a left action by A1 and a right action of A2. Each of the left action and the right action individually have to satisfy the representation property that I discussed here, except that being a bimodule, the action of A1 and A2 have to commute. So this allows you to systematically work out all the representations localized at the junction as well. So the mathematics of tensor category just helps you to organize all of these physical data in a very simple way. So let me not talk about this example. It's trivial. So you can consider excitations localized between the electric charge condensate of the Toric model and the magnetic charge condensate. So using these methods that I described, if you try to compute it, then you will find that a Majorana mode can be trapped here with quantum dimension √2. So this is just some computations. Let me not bore you with that. But this is more interesting. So we all know in either if you're familiar with modular tensor category or with CFTs, there's this famous Verlinde formula, which relates for you the S matrix and the fusion rules of the primaries of the anyons. So here we can easily derive a Verlinde formula that is good for these excitations at the boundary at a gapped boundary. So let me try to at least say two things. I know I'm running a little bit out of time. So the first thing is the thing underlies a Verlander formula is the fact that doing fusion and doing braiding is interchangeable. So if I consider an anyon from the condensate 1, so I have some confined anyon here running lying at the boundary that I call X, and then I have an X is between condensate A1 and A2 is at the junction, and then I have another anyon that is at the junction between A2 and A3, and I could consider taking a condensate, condensed anyon from A1, pull it out, create it because it's not conserved, so I could create one that moves into the bulk, move around X and disappear from X. Move around X and disappear in A2. This is possible as long as C is shared between A1 and A2. Then I could create another anyon, the same C, from A2, and then move around Y, and then disappear into A3. That is again possible if C is also shared between A2 and A3. But these two processes should be the same as if if instead of breaking this anyon line in A2, leave it unbroken, and then just move C across it, and then fuse a strength A2 to a very shorter and shorter segment until X and Y fuse together to give you Z. So if you consider these two processes to be equivalent, then you will find that you would be this braiding gamma is the half braiding of these condensed anyons with the confined anyon would give you a representation of the fusion rules of these anyons, exactly like the S matrix is a representation of the fusion rules of the primaries in a CFT, and so that would allow you to derive this so-called Verlander formula, where you relate the fusion rules to braiding to the braiding between anyons. So the underlying physics of the Verlander formula could be thought of as that braiding and fusion, the order of things, is interchangeable. So you can derive some very powerful results out of this set of physics. So let me say a few. So you can also work out ground state degeneracies when you have different boundary conditions, but this is so this is straightforward, and there's also applications of in quantum computations. So I want to say a few words about that, and that is we know that people like Kitaev, they propose that we can do quantum computations using a topological model. And the idea is I can create different quantum states by, create different quantum gates by taking anyons and allow them to braid with each other. For non-abelian theories, this braiding is a non-trivial rotation, a non-trivial matrix, and therefore I could supposedly create any logical gates based on this topological theory. But in general, practically, it's very difficult to have non-abelian topological order realized in experiments. And therefore, it's just much easier if I can start with an abelian theory and I consider non-trivial interfaces and non-trivial edge excitations. And so if I can make use of these things and braid it somehow, then I would be able to create logical gates without actually realizing a non-trivial topological non-abelian theory. I could start with some abelian stuff and then create some defects and interface and braid those interfaces. And so this is one of the reasons why people got interested into looking into defects and interfaces and so on. But let me also say a few words before I end about its connections to modular invariant CFTs. So as I mentioned, when you look into a collection of anyons that can condense together, it is actually proven mathematically that they are in one-to-one correspondence with modular invariant. that can condense together so that it becomes a gapped boundary, I should say. But you can always fold the theory, and so every condensable algebra actually corresponds to some modular invariant, and they are precisely so. If you so we know that rational conformal field theories, the primaries can be organized by. The primaries can be organized by I shouldn't say modular invariance. I meant modular tensor categories. So this is the work of, I think, first by Moore and Seiberg, that shows that the primaries in the rational CFTs can be organized into modular tensor categories. But then if you want to construct a modular invariant CFT, then you have to pick the correct, you have to pick from all the possible primary sectors. You have to pick a combinations where Zij is some integer. You have to pick the multiplicity of certain sector judiciously, so that together the characters would form a modular invariant. And so if you think of these different sectors as being different sectors in topological order, or just view it in terms of modular tensor categories, then each of each of these Frobenius algebra that I just described basically allows you to find an individual modular invariant of a rational CFT. Then what about these confined sectors? What about these confined sectors that we have spent so much time computing? These confined sectors that that we have constructed, they correspond to topological defects in this modular invariant CFT. They're in one-to-one correspondence. So by looking up, looking for all of these representations of Frobenius algebra, you are basically classifying modular invariance CFT, and also classifying the topological defects, topological lines that shows up in a modular CFT. And so these things have been considered before, for example, in Zuber, Petkova in the 80s. And so one could see, one basically, these line operators that are topological defects, they commute with the Virasoro operators, and then they could be written in this particular way in terms of states in the Hilbert space. And these states, of course, they have to appear inside the modular inside the modular invariant Hilbert space. And the coefficients here, we show that they are precisely these so-called half-linking numbers that I showed you before, a few slides before, when we derived the defect-Berlinde formula. So these things that we obtain purely based on data in a tensor category, they just show up in the CFT. They're exactly the same thing that people knew about in CFTs. And you can work them out completely systematically just based on data of the modular tensor category. And in fact, if you look into interfaces, we also looked into excitations localized at junctions between two gapped boundaries. And they correspond to interfaces, topological interfaces between two modular invariant CFT. So they are also in one-to-one correspondence. So these are just some examples. And why are these topological defects interesting? So more recently, people stared into these topological defects again, and they realized that just like you can think of them as symmetry, because they commute with all the Virasoro operators. Then certainly they commute with the Hamiltonian, and so they're just like symmetries, except it's not a group symmetry, because the fusion rule between these topological defects in general don't form a group multiplication. In general, it's some non-trivial fusion algebra. So some people call this algebraic symmetry. More recently, people call this categorical symmetry. So it's just that there's some high dimensional generalization or higher form generalization, but people are already realizing that they give you further constraints on RG flow. They protect fixed points. They might be a way of characterizing different universality classes, a different way of characterizing universality classes. So these symmetries are important. They hold in them lots of interesting physics. In 1+1 CFT is relatively well understood. As we see, we have some complete set of mathematics to deal with this. But in high dimensions, the situation is pretty much open. Very little is understood about these objects. So let me summarize quickly. Sorry, I run over time. I reviewed for you the notion of modular tensor category and its central role in characterizing topological orders, particularly in 2+1 dimensions. And we talked about boundaries, interfaces that are characterized by this notion of Anyon condensation, which give us a web of different theories. They are very deeply connected to two-dimensional CFT. And pretty recently, people are starting to generalize it to higher dimensions. They realize that it is actually possible if I consider also anyons with different spins to condense. Well, of course, if they have non-trivial self-statistics, they can't condense alone. You have to pair them up with something else. So for example, if you have a so-called fermion condensation, what you really do is to pair it up with some other fermions to form Cooper pairs to condense. So tomorrow, we're putting out a paper that completely characterize how fermion condensation works. But so there are lots of generalizations either to other possible ways of condensing anyons to characterize this web of theories, to characterize these topological defects, or generalize it to high dimensions to understand these and understand the defects that follows from it. And so there's some high dimensional generalizations of these ideas. You can see these latest papers by Galto and company. And so this is a very rich subject that is to be explored. So I hope I gave some understandable introduction, and thank you very much for listening.